Wave motion is how light and heat travel, how sounds travel, how Wi-Fi and phone signals travel, how energy and water travels, and loads more. So to understand waves is to understand much of the world, which is kind of what physics is about, but luckily, waves are easy to visualize and you won't have any difficulties. All waves carry energy. That's what all waves have in common. Waves don't carry the same amount of energy and can be very different. But the thing that every kind of wave has in common is that carrying of energy. Here are the most important and useful ways we have of describing waves. By imagining that you are lying back on a hot, sunny beach somewhere, we can understand these measurements. The time it takes, in seconds, for each individual, single wave to arrive at you is called the time period of the waves. Time period is shortened to capital T and measured in units of seconds. The actual length between the peaks of the waves, in other words, the length of each individual single wave, is called the wavelength of the waves. Wavelength is shortened to the Greek letter L and measured in units of meters. And the height of the waves, from the middle to the top, is called the amplitude of the waves, shortened to A and usually measured in meters too. Don't forget, from the middle. Tsunamis have enormously high amplitudes. So next time you are on a beach, make sure you point out all these different measurements to whomever you are with. They will really like it. So after your day at the beach, your t-shirt has sun cream and Bucky on it, so you decide to put it in the wash when you get home. The washing machine vibrates, and the number of vibrations each second, or the number of waves, in this case sound waves, moving past a point each second, is called the frequency. Frequency is measured in units called hertz, named after a guy called Heinrich Hertz. Heinrich Hertz's first love was carpentry, making stuff with wood, but he then got interested in messing around with electrical circuits, bits of wires and primitive electric devices. This was the Victorian age, and electric circuits were pretty new and high-tech. People already knew that electric circuits had a magnetic field around them. If you put a compass next to your phone, the needle will turn, but Hertz realized that as well as this, there were invisible waves coming out of the circuits. He called these electromagnetic waves, but he wasn't entirely sure of what they really were or if they had any use. But he was the first person to realize them being there. The Scotsman Jimmy C. Maxwell then realized that these electromagnetic waves were light waves. So light is known as an EM wave. And the frequency of a wave, the vibrations per second, has the units of hertz, in Heinrich's honor. The reason why a beam of light doesn't look like a wave, by the way, is that the frequency of light waves is insanely high. The vibrations per second, or frequency, is so great, a ray of light just looks like a blur of color. It's a little bit how you don't see the waves on a guitar string when it's strummed, you just see the string blur a bit. The speed of all kinds of light wave, in air or space, is 3 times 10 to the power 8 meters per second, and this is on the data sheet, along with the speed of light waves in materials other than air or space. Similarly, the speed of sound waves in air is on the data sheet, along with the speed of sound waves in other materials. Of course, sound waves cannot travel in space. When sound waves travel at different speeds, we experience them very differently. For example, sound travels more than 3 times as fast in helium gas than it does in normal air, and that's why someone's voice sounds very different if they've inhaled helium. Similarly, the sound of your own voice when you hear a recording of yourself is definitely different to the sound of the voice that you yourself normally hear. The sound of your voice that you normally hear, and are most comfortable with, is sound that has actually traveled through bone and your head, so the speed is different. Your voice recorded is what everyone else actually hears you as. The only type of light that is visible to humans is a kind of light that we, well, unsurprisingly call visible light. The other forms of light in this EM spectrum are invisible, but still very useful to us. Radio waves have the lowest frequency or vibration rate. This means they also have the longest wavelength of all the kinds of light. Radio light is used for communication. Microwave light is also used for communication, especially with mobile phone signal and also satellite signals. One time, a soldier was standing in front of a microwave transmitter when it was on, and a chocolate bar in his pocket melted a bit. A boffin heard about this and invented microwave ovens. Only a really specific frequency of microwave light makes water molecules hot, however, so there is no danger at all about the microwave light coming into your phone cooking your brain. If the exam asks for a use of microwave light, don't just answer microwaves. Say microwave ovens or cooking food instead. Infrared light is the kind of light that warm-blooded animals like us give out. Some snakes see in infrared light, to help them catch rodents at night time. Night vision goggles and thermal imaging cameras can detect infrared light, body heat, given off by people. These are used by mountain rescue services to spot injured climbers up in the mountains, when otherwise they would be very difficult to see. Similarly, when the Americans were hunting the Taliban leaders in the snowy Tora Bora Mountains in Afghanistan after 9/11, the heat signature from the mouth of caves they were hiding in gave them away on the thermal imaging cameras, showing up particularly clearly against the cold, snowy background. Visible light is the main type of light given out by our star, the sun, so it's not surprising that our eyes have evolved to pick this up. The sun also gives out heat or infrared light, which we use to dry clothes when we hang out the washing, and also ultraviolet light, which comes next. Ultraviolet light has a high frequency. The higher the frequency of a light wave, the more energy it carries, so the more dangerous it is. UV light can burn skin and cause enough damage to start skin cancers. But UV is also useful. For example, there are some inks that glow brightly when UV light is shone on them. These are called fluorescent inks. They are used in some highlighters, bank notes, security pens, and rave makeup and face paint. If you haven't tried it, you don't know what you're missing. Buy some and get down to DeVito's. X-ray light is energetic enough to get through muscle and soft tissue, but gets blocked by bones. This makes X-ray light very useful for taking medical photographs to show where cracked bones are. Gamma light is the highest frequency, shortest wavelength light. It's very dangerous because it carries so much energy. It's used for killing cancerous tumors in a process called radiotherapy, but it's also used to turn quartz, a cheap, common, and not particularly pretty crystal, into different colors. So if you've ever wondered how you can get a lovely ring with a sapphire, emerald, or ruby, so cheaply for your better half, then it's because it won't be sapphire, emerald, or ruby. It's going to just be quartz that has been irradiated to hell. Not that there's anything wrong with that. Seedless oranges, satsumas, and clementines were also made thanks to gamma light. The originals of these fruits always had seeds in them, but by hitting these seeds with gamma light, before they were used to grow new plants, mutations were caused in some of those new plants when they grew, and they were seedless. Think of that next time you are tucking into a cheeky wee satsuma. Radio wave light and microwave light need an aerial to pick them up, as they have such low energy. Infrared light can be picked up a thermal imaging camera, a really old-school thermometer type called a black bulb thermometer, our skin, or an electronic component called a photodiode. Ultraviolet light can be picked up by fluorescent material or a photodiode. X-ray light can be picked up with photographic film or by a photodiode. And gamma light can be picked up by photographic film, a bit by Geiger counters, or by a photodiode.